Hello, calculus class. This is the notes for week number 4. We're going back and talking about concavity, concave up, concave down kind of thing. In class, we kind of joked about some different ways to talk about it. So I'm just going to draw a rough sketch before we get into that example that's drawn there, or that's in that function there. So the idea of concavity, if we have this function, it looks something like this. We talked about the idea of holding water. So like this part right here, where if you poured water into it, it would hold in this bowl. That would be concave up. The other idea right down here, this part of the graph would be concave down because the water would fill or spill out. Some of you like this idea of putting little smiley face in there. So big smiley face, concave up, upside down, frowny kind of thing, concave down. Whatever floats your boat, whatever works for you. This is the idea of what we're talking about. Talking about concave up or down. So, looking at this example here. When we talk about concave up or down, the big ideas of the notes are this. We're talking about the second derivative. So the derivative of the derivative. If that second derivative is positive, meaning greater than 0, that tells us the function is concave up. If that second derivative is negative, meaning less than 0, that tells us that the original function is concave down. So this is what we're looking for. So the first thing is getting to that second derivative. So we just start with taking the first derivative. Just doing some power rule, 3x squared minus 4x minus 6. And then take the derivative of the derivative to get us to the second derivative. So we get 6x minus 4. All right, there are things called inflection points. That is where the second derivative is equal to 0 and or where the second derivative is undefined. Our second derivative is not going to be undefined, but we can set it equal to 0 and solve. So 6x, add 4 to both sides, divide by 6. What we get is x equals 4, 6. I'm going to clean that up a little bit, 2/3. So this is our one and only x value, that is still getting better at writing with this pen, inflection points. Boy, that's terrible writing, but whatever. You can listen and see it. Inflection points. Okay, we take any and all of our inflection points. We throw them onto a number line. We only have one, so it's 2/3. Great. What we are looking for is this. We want the second derivative to either be positive or the second derivative to be negative. We know where the second derivative is equal to 0. So what we do is we test some numbers. I'm going to pick 0 and I'm going to pick 1. And we're going to test them. Again, we're looking for the second derivative to be positive. So we take those test numbers, the 0 and the 1, that's on either side of our inflection point, and we plug them into the second derivative. So f of 0 into the second derivative is negative 4. Second derivative at 1, we'll plug 1 into the second derivative. 6 times 1 minus 4 is a positive 2. Now, we don't care about these numbers. I don't care about the 4 or the 2. I care about the negative, and I care about the positive. So, when we tested 0, it was on this side of our inflection point, meaning x value is less than 2/3. This test number made our second derivative negative, so that means our function is going to be, I'm just writing it shorthand to keep this video quick, concave down for all the x values less than 2/3, but when we talk about interval notation, going from negative infinity up to 2/3. When we tested 1, that was on this side, that was for x values more than 2/3. Our second derivative was positive, so that means our function was concave up. Again, x value is greater than 2/3, but with the interval notation, 2/3, starting at 2/3, going to positive infinity. This is the idea of what we're looking for our answer. And that's a quick rundown on intervals of concavity. I hope this helps. I hope everybody's doing well. Take care.